The big Muto cutting plotter is gone now. I gave most of it to the scrap metal collector, but I kept the best part for projects like these. It's a 2-meter linear actuator with a DC servo motor. The main belt is an absolutely rigid stainless steel one, which is something that I've never seen before. And there are also stainless steel inserts in the aluminum profile as running surfaces for the 8 roller bearings of the carriage. The motor is a 30-volt one by Tamagawa, and the rotary encoder has a supremely accurate 4000 pulses per revolution. Operating a DC servo motor is an ideal opportunity to try myself in some PID tuning. But I also wanted to get this over with ASAP, so I just used an Arduino and several existing libraries. With those, it's a piece of cake to set your tuning parameters or drive to a location. But with a 100 tuning, our cutting plotter wouldn't produce particularly satisfying cuts. What we are getting instead is an unstable system, and that's a classic indicator for a proportional gain constant that's too high. So let's reduce the proportional and crank up the integral component. I didn't debounce that push button at all, that's why it takes a couple of tries every time I press it. The result is looking better, but there is still overshoot visible. The integral term responds to the amount of time that we spend out of position. That's why it introduces overshoot. So let's lower that one as well and see what's happening. The jerkiness mid-travel is caused by the bouncy button, and the continuous noise is the PWM carrier frequency. Apart from those two things, the movement looks pretty good. The derivative term works with the error slope. For example, if we are closing in on our destination too quickly, it anticipates an overshoot and slows down. In real-world applications, the derivative term is rarely used, because A, the P and I terms are adequate for most tasks, and B, the derivative term can be difficult. For example, if you're having noise in your system, D will try to counteract that with rapid and violent output changes, which in turn can have a destabilizing effect. So rather than trying to tame the derivative, I went straight ahead and implemented the 0.005 mm resolution digital readout. Which of course was a piece of cake all over again. Now the PID controller is great for balancing things like an inverted pendulum, for example, but right now I've got another idea. Camera sliders can be pretty damn expensive, and even if you're willing to spend $200 on one, you're in for a plasticky cheapo. This one's plenty long, plenty rigid, programmable, and it's almost already done. It just needs another motor, because PID is just not made for slow, uniform movements. With a lot of tuning you can get close, but constant velocity is absolutely not guaranteed. But that's something you need for your time lapses. With voltage adjustment you can't go slow enough without risking a standstill. And a stepper motor needs a lot of micro stepping and probably frame blending in post-processing too. But given those things, and some proper timing maybe, you can have high-end results.